what we're going to do is we're going to continue to try to come up with equations. Now, to come up with an equation is actually a mathematical procedure known as a regression. It's known as a regression. Just want you to know that everything that we do in the next 20 minutes kind of is with that theme. Again, the theme is a regression, which is to come up with an equation. Let's back up just one step to try to remind you guys from yesterday that anytime we have a percent change, and of course percent is the key idea, you're always going to be able to model that with y equals ab to the x. Now, y equals ab to the x is a very simple equation, but it can do some pretty powerful things because, well, it deals with percentages. Just so you can get that word on your paper, we're going to use exponential regression. Exponential regression to analyze a table of data. Again, what's a regression? It's the process of coming up with an equation. Okay, so everything has that goal today, to come up with an equation. Now, this first one we're going to do here, this is kind of a classic. It deals with money. And basically, if you scan the paragraph, we've got somebody that's young, and they decide to put some money away. Basically, take $2,000 and invest it for a long period of time. Now, we would call this simple interest because basically you're not adding anything else to the money. You just put it in the bank. Actually, you had to put it in like an investment, which would be like a mutual fund. But it's going to sit there and, of course, grow, and grow. Okay, let's get into the problem. The first thing to do is just to kind of visualize it. And to do that, you honestly just need to graph your numbers. I want you to notice when you graph your numbers that the scale that I've given you for the x-axis is obviously different than the y-axis. The y-axis scale goes by 10,000. So don't spend too much time trying to be too perfect. If you're going to plot these points, the first couple points are really close to the bottom. And that's okay, because your scale goes by 10,000s. You're not going to be able to see much change until you start getting up to about 20 years. Okay, once you get up to 20 years, your dots start to spread out a little bit. Now, as you get into this a little bit more, you might start to notice a certain pattern, a certain shape, honestly, a shape that looks like, well, exponential growth. Eventually you say, yeah, I'm not that surprised because, well, if something's going to increase by a percentage, which is definitely what's going on in this problem, if something's going to increase by a percentage, it's going to be in the shape of exponential growth or exponential decay. In fact, if you want to draw that graph, just kind of, as best you can, sort of connect the dots, you can start to see that familiar shape, that exponential growth. Okay, so we're in the right place. What place are we in? Well, we're in the percentage place. Now, what I want to do next is I want to take you guys on a little bit of a journey to come up with this percentage. This is step 2. Just so you know, in step 2, we're going to predict the exponential model. That's kind of fancy talk for we're going to try to come up with a, b to the x. We're going to try to come up with this equation. Now, to do that, we had a technique from yesterday. And even if you're a little confused, we kind of go over it again. The technique is to divide. Now, you would need like a regular calculator. I hope that you have that handy. These little boxes are supposed to get you to divide, remember, the second number by the first number. So like 3,000 divided by 2,000. But normally, it's wise to divide a couple places. So you can divide 7,800 by 5,000. And I hope you can see what we're suggesting here. We're just going to divide, like I said, at a few places. Now, as you divide these numbers, don't be shocked that they're not all the same. That's because this is just data. It doesn't mean it's like perfect. But even though they're not all perfectly the same, they are very similar, aren't they? So what we want to do is we want to try to come up with like the average. Now, I didn't do this with you yesterday. Yesterday, we just kind of looked at the numbers and said, hey, that looks pretty close to blank. But today, instead of saying, hey, that looks pretty close, let's actually average the numbers. Now, this is just a good old average. That means you're going to add all those numbers. It's just 4. So you're going to add those 4 numbers and divide by 4. That's the next box. So again, take those numbers, add them up, and divide by 4. Or if you're confident that you can do that, you're welcome to grab it from me. You get 1.5375, which is really close to all 4 of those numbers. Again, 1.5375. Okay, now here's the one part of today's lesson that I get it if it can be a little confusing to kids. I did do it one time yesterday, and if we don't do it, I'm not really showing you the full truth. That is that you need to take this number, 1.53, and realize that it's per 5 years. That's not good. We don't want it per 5 years. We want it to be per year. That's because we want to have a percentage that is per year. Yesterday, we took the number and we fixed it. We fixed it. How do we fix it? Well, you have to use a reciprocal or a root. Okay, and I don't want you to get like too worked up about this, but if I don't show it to you, I'm not kind of giving you the full truth, which is you have to take this number and you have to fix it, not by dividing by 5. Okay, I don't want to divide by 5, but I want to do a reciprocal of 5. And notice that I do that reciprocal as an exponent. We did it one time yesterday in the very last problem. Maybe you remember how we took the world population and we did a reciprocal. I think we used the reciprocal of 50, 1 over 50. But here we're going to use 5 because it was every 5 years. Now, the important thing is that you realize that the number that I get over there on the right-hand side, I'm going to go ahead and round it to just 1.09, just to kind of keep things a little simpler. That number I get is the base. It's the base. And since it's the base, and this is something I want you to kind of grab onto, I can use it in my equation. Like with full confidence, the base is going to have to be 1.09. Because that's always what you get after you do this division. And in this case, I also had to do a reciprocal. I forgot to flip the screen, but let me show you what I did here. I took 1.09, I filled it in as the base. And just take a deep breath. What we're trying to do is we're trying to come up with an equation. Okay, it took a little bit of work, but right now we know that the base is 1.09. Another little side note that's important for the next couple days is that whenever you have a base, you also can get a percent. You can get the rate. How do you get it? All you have to do is take that number and subtract the number 1. Some kids just do this mentally. Some kids, you do it on a calculator. But if you subtract the number 1, you get 0.9. What is 0.9? It's 9%. It's 9%. Okay, that means that the money is going up 9% every year. Okay, it really is going up by 9% every year. We're trying to come up with an equation. We need a starting value. Don't make this too hard. Your starting value is in your table. Your starting value matches with 0. So I don't see any reason why we can't say that 2,000 would make sense in our equation. Okay, so we have what's known as an exponential model. Now, just so you know, we came up with that exponential model, as I like to say, by hand. We kind of just thought about it using some basic division, not any fancy stuff like Desmos. You see, Desmos can also do a regression. It's pretty nifty. I mean, that this stuff is right at our fingertips, again, is pretty good stuff. So we're going to have Desmos, so to speak, do the same thing. Now, if you haven't yet, make sure that you fire up desmos.com/calculator. And I need to remind you of something that we did do a few times this year. We haven't done it every day, so it might not be right on your fingertips, but we have to basically get the data into Desmos by adding, in the upper left corner, by adding a table. Okay, now once you add a table, it's pretty sort of common sense here. We're just going to type in our X and Y values. Desmos is pretty smart. It notices that your X values are going by 5s. So if you just keep hitting enter, it will do the typing for you. Again, we're going to type in the X and the Y values. If by chance I missed you, remember we hit the little plus sign in the corner and we went to add item table. Add item table. Now, it might be nice if we could see what was going on here. That is, that if we could see these points. The reason we don't see them is because the window is not, I missed one, didn't I? The reason we don't see these numbers is because the window doesn't really match with these big thousands. So we'll fix that next. As we've done in other times, if you hit this little wrench up here in the corner, you can change the window. This is actually important, but all you got to do is make your X values match the years. So I'm changing the X axis to maybe be like 0 through, how about 0 through 50? I don't have to stop right at 40. I can go a little bit beyond. And then make your Y axis go like 0 through, well, I don't need to stop at 75,000. In fact, I know a little something. I'm going to go the whole way up to 200,000. I'm going to go up to 200,000 so that, well, again, we can see something. Okay, so Desmos has kind of done what we've done so far, which is to basically graph some data. But now we're ready to tell Desmos to do something that we have done, but we didn't do it quite as good. We're going to have Desmos come up with the equation. Now, to come up with the equation, you basically have to tell Desmos, hey, what is y equals ab to the x? But if I type y equals, it's going to try to like graph something. So instead, I need to use y sub 1. Now, to use y sub 1, I just have to type y1. Also, instead of using the equal sign, remember you use the tilde symbol. The tilde symbol is on your keyboard. It's in the upper left corner. Let me just type it out, because basically what you have to do is tell Desmos, hey, I want to know what y equals ab to the x would be. But instead of using x, I will also use x sub 1. The reason I'm using y sub 1 and x sub 1 is because that's where the data is put, again, in your table. Okay, how's that going for you? I typed y sub 1 tilde ab to the x sub 1. And we end up with a gold mine of math information. We basically end up with the equation. You have to look at the little specks down there in the box. Okay, now if you're looking at those specs, you might be saying, that looks kind of like what we already did. Yeah, in fact, that's because we did a pretty good job. But Desmos has just given us the actual answer. And if we put that down as our regression equation, it looks like we're going to use 2,147. So it's a little bit more than 2,000. But if you look at the base looks very similar to what we came up with. I'm going to use one more decimal place just because I can. So we'll round it to 1093. Very similar equation to what we came up with by hand. Remember, if you have the base, you can get the percent. I want you to look at numbers like 1.093 and say that that's really just the same as 9.3%. Let me flip it back to Desmos because we're going to use it to kind of finish. And that way, again, if you got maybe a little lost, you can see what we did again. Whenever you do a regression, you always use y sub 1 and x sub 1. That's because that's where you typed in the data. You also use a tilde symbol. Tilde tells the Desmos to actually calculate. And then down here in the box, I have my answers. Now, it doesn't do much good to come up with these answers if we don't do anything with it. And that's kind of like question 4, which is to do some predicting. You realize that you can just drag to 50. Basically, you can go to 50 years. And it looks like in 50 years, I'm going to have $182,000. That's nice. So again, I can just drag to 50 and I get $182,000. I could also, kind of like we did yesterday, I could also plug in. I could plug into my equation. Now you would just want to use like a regular calculator. I'm using the Desmos calculator so you can see it. But if I plug in 60, of course, use 60 as an exponent. Now I have $445,000. So again, I have an equation. Let's do something with it. Let's plug in 50 and or 60 and see how much money you have. Now, honestly, this is very realistic. If you took $2,000 and you dropped it and you let it sit there for a long time, you're going to end up with a decent amount of money. Okay, that's because we have exponential growth. And if you didn't do so already, you can take your graph and you can kind of like finish it, because your graph eventually starts to go almost vertical. And as it goes vertical, well, that's why we have $445,000. Now I have one more thing that I want to show you. It might be the most interesting thing this morning. And I do mean that. If you just hang in there with me, there's an interesting pattern that happens anytime you have money that's growing. It's called the rule of 72. Just kind of curious, and I'm serious about this, in your finance class, what do they call that? Personal finance? Do they talk about the rule of 72? Does it at all sound familiar? I'm seeing some yes or no. It is very interesting, and I'm not making this up. The rule of 72 tells you how long it takes for your money to double. It tells you how many years it takes for your money to double. I'll just call it years to double. And all you have to do is take 72 and divide it by your percentage. All you have to do is take 72 and divide it by your percentage. Now for this problem, I hope you get the idea that 9% was that magic percentage. We found it two different ways. So what happens if you take 72 divided by 9? This is one of the times in math where you actually don't want to change it to a decimal. That doesn't happen much, but that's the way the rule of 72 works. You don't change it to a decimal. Well, you get 8. What's 8? Well, 8 years for your money to double. Do you believe me? Or do you believe it? 8 years for your money to double. Let's go back to our pretty cool looking graph here. Where were we at? How about 50? 50 was kind of a nice place. We had how much money? $182,000. Now, in 8 years, well, how much money do I have? What's double of 182? It's just about 371. It's almost perfect. So in 8 years, 182 went to 371. Now, did you see how far that I moved that dot? It went up, up, and away. How about back here? How about back here, like at 20 years? At 20 years, I only have like $12,000, if I can get it there. Now, what's double of $12,000? Well, it's only about $24,000. It's actually 25. It's still double. Okay, the rule of 72 works for any 8 years. But when would you like to double your money? Would you like to double it down here where the graph is kind of flat? Or do you want to double it up here where it's almost vertical? Okay, well, the point is that it takes a lot of time until you get to that vertical part. But then your money starts to double in a very exponential way. So the rule of 72 works for any amount of 8 years. Okay, but it's super sweet when it's in those big 8, those later 8 years. Now, there's 3 problems on the back. The first one is intentionally much like the one we did because I'm trying to set you up for success. In fact, a lot of kids will be successful with that problem even right now. I encourage you to be one of those students. After you finish that first one on the back, then I have 2 more that start to deviate a little bit, trying to get you to go to a new place. You're probably going to have to work on some of that more outside of class. But right now, why don't you see if you can be successful with it, with that car problem. Just by the way, notice that the money or the value of the car is going down. Notice that the value of the car is going down. Okay, that makes sense. And that's why you're going to end up with the type of answers that you get